Thank you very much. I think maybe like this. Okay. So yes, I'm Ugo Dal Lago. I'm honored to have this wonderful task of presenting the session, the first of the two sessions about semantics at POPL. So that will take place tomorrow morning, exactly as in the same slot as Synthesis 2 at Avenue 34. So let me just tell you a few words about semantics. Maybe not all of you are familiar with program semantics. So what is it? So take a program P in your favorite programming language. P is ultimately just a sequence of symbols, right? You can take it as a string. And by itself, this string does not tell you too much about the behavior of the program or what this program is supposed to do or compute. So program semantics is supposed to be a subfield of programming language theory which tells you what the meaning of P is. And actually, as it is, program semantics is not just one does not provide just one way of giving meaning to P, but actually many. You have probably heard of operational semantics, which is just a way to design relations, putting programs and possible results, values into correspondence. So to design correspondences between programs and possible values. So operational semantics is simple and typically designed in an algorithmic way, so very effective, but it's not compositional. Namely, the meaning of a program is not defined in terms of the meaning of the subprograms. Sorry. Then, alternatively, you can go towards what people call denotational semantics, which is instead mathematically inspired. So, programs are assigned a mathematical object in some domain of some kind. There are actually so many ways of building these domains for different programming languages, or even for the same programming language. The nice thing about denotational semantics is that it is compositional in nature. So, an application of a function to an argument is assign a meaning which is typically, the meaning of the function applied to the meaning of the argument. So it is compositional in nature. But this is not the end of the story. You can also take types or logics as a way to give semantics to programs. Of course, this is often, let's say, inspired by logic. Take, if you know something about that, the carry-hour correspondence, in which types are designed with intuitionistic logic in mind, for example. But it is still, on top of that, compositional. This is another alternative way to give the semantics to programs. Actually, there are type systems which are even designed to be not to be a way to do type inference or type checking, but they are designed as a way to give semantics to programs. For example, intersection types. And then there is like all the whole world of equational theory and rewrite theory. And in rewriting or equational theory, you want to put different programs into relation by way of a symmetric or a not necessarily symmetric relation in the case of rewriting. And the evaluation of programs is done this way by a form of textual replacement. So some parts of your programs are replaced by equivalent ones. And when this process is oriented, rewriting takes the place of can take the place of the operational semantics. By the way, this is not at all the end of the story, because there are so many other ways to give semantics to programs. But these four types of these four alternatives to give semantics to programs are, by the way, those that we will see tomorrow in the session. So let's take a look at the papers. So the first one is called Typebased Approach to Divide and Conquer Recursion in COG. It is by some guys in Purdue and University of Iowa here in the US. So what they do, by the way, this is this can clearly be ascribed to the style of semantics at the bottom right in my figure, so type systems. So the topic here is type theory, in particular the kind of type theory on which COC is based. COC is, I think, a tool that many of you knows. And the point with this type theory is that it must ensure that programs are terminating, because this property is necessary for type checking, to maintain type checking decidable. The point is that the kind of recursion that you can directly write in the type theory of COC is very restricted. It is a form of structural recursion. If you don't know about it, it's a form of primitive recursion. So it's not the kind of recursion that it is easy to use in practice. For example, algorithms like merge sort or quick sort, well, they are not structurally recursive. They are recursive, but in a different sense. So this paper shows that without changing the theory, staying exactly in the same type theory that COC uses, you can go beyond structural recursion and get something closer to a divide and conquer style of recursion. Good. So this is the second paper. It is by a couple of guys that actually know well, from Bologna and from Pisa in Italy. So it is about rewriting. And the idea is that, one would like sometimes to go beyond the classical rewrite theory. Why? Because classical rewrite theory does not support well a quantitative form of reasoning, because the two objects that rewrite the theory and equational theory put in relation, well, they are just deemed equal. As soon as the two things are slightly different, well, they cannot simply be rewritten one in the other. So in the kind of viewpoint that this paper promotes, rewrite is not for free. You have to pay to go from the left-hand side to the right-hand side. And that's a good way to capture differences between programs, difference in the behavior of the programs you want to compare. And this accounts for similar but not equivalent programs. And they show a lot of nice examples about that. So the third paper is about game semantics. So it's a denotational. This is a denotational way to attribute meaning to programs, but it's also operational in flavor. Let me tell you why. So game semantics is a semantic framework in which programs are interpreted as strategy in the sense of game theory. It is a framework which has been extremely successful and applied to so many different programs, obtaining unexpected results like full abstraction, if you know about it. The authors here are interested in a concurrent form of game semantics, and this is very challenging for reasons that the authors will explain to you tomorrow. And the peculiar feature of this paper is that they managed to attribute, to give game semantics to a concurrent higher order programming language by way of something called Petri nets. Maybe some of you know. This is a classic model of computation, very nice. It is causal in structure, by definition, and they managed to do it for a higher order programming language, which is quite remarkable. Okay, so the last paper, it's about denotational semantics, and in particular about category theory. Category theory is a very successful framework in which programs can be interpreted. Actually, it's also a way to classify different semantic frameworks as for their structure. And it's an algebra of composition, if you like. That's an algebra of structure of functions. And particularly, there's one line of work which is quite hot in the last 10 years. It has been quite hot, called string diagrams. In string diagrams, you reason graphically about programs by way of some kind of equations on graphs. And what the authors do in this specific paper is that they capture, by way of graphical calculus in the style of string diagrams, The task is calculus of relations, which is a very popular and very powerful way of reasoning about relations, which is, by the way, useful also in semantics. Thank you very much.
Thanks, everyone of you. Thanks all of you coming here, join the private session. It's quite nice, and the talks are very inspiring. See you around.